exploration, socially aware navigation, or multi-agent coordination, and because of its basic requirement for several tasks, it has been solved in many ways for many years. Classical approach to solve this problem is to use as systems which are composed by several modular components which interact between them. So we have some modules that extract information from the environment and some other modules that use this information to actually plan and execute collision-free trajectories. But more modern approaches are actually based on machine learning techniques, are data-driven, and are trained in an end-to-end manner. So for the collision avoidance being solved using machine learning techniques, we have two main paths that we may follow. First is supervised learning, and then it's reinforcement learning. Supervised learning collision avoidance policies are trained using databases which are actually states the robot see in the environment and are labeled with actions that the robot should take given the state of that sample in the database. And the problem with this approach is that the capabilities of the trained controller are actually bounded by the ability of the supervisor, which means that the neural network, for instance, if we train a neural network, won't perform better than the person that performed the actions to actually make the database. However, if we take the approach of deep reinforcement learning, we can get around that because we are not bounded by any supervisor, and we are actually training a controller with experiences that the robot is actually when the robot is interacting with its environment. Now, collision avoidance through reinforcement learning have been solved. There are several works in the last years that tackle this problem. However, there are some challenges that are usually not addressed in these cases. First, that there is really constrained robot perception in actual scenarios. For instance, with indoor service robots, there is a big mismatch between simulations, because policies are usually trained in simulations, as train a collision avoidance policy directly in the real world would be really risky. And there is performance issues when the policies are actually tested in real world environments, which are challenging and really different from the training environments in simulations. So we wanted to tackle these problems. So to model the collision avoidance problem, we selected the Pepper social standard platform, because the Pepper robot actually has a constrained perception range. It is a robot that is suitable for testing the issues that are not actually often addressed in the problems, in the works that have solved collision avoidance before. So we frame the problem in the standard reinforcement learning framework by modeling the environment as a Markov decision process. Namely, we define a state space, an action space. Transition dynamics are directly used as, since we are training the policy using gazebo simulator, and we created an ad hoc design function for the reward. So state space, we try to use most of the sensors available in the Pepper robot. So we are usually we model the problem to use the depth image coming from the depth sensor in the head of Pepper. We also used lesser range measurements coming from the lasers that are present in the base of the omnidirectional base of the Pepper robot. And we provide some feedback to the policy by using instantaneous speed estimations using odometry. For the action space, we just provide velocity commands to the omnidirectional base of Pepper. As for the reward function, as you can see in the slide, in the left side we have the one part of the reward that actually encourages the robot to move forward through traversable paths by encouraging it to have high x-axis velocities and penalizing high rotational speeds, so the road actually doesn't get stuck spinning. For the as we model the environment with episodes, we actually end up episodes if if the robot collides with any obstacle, or if the robot reaches a certain time step limit. And also there's a punishment signal, as you can see, which is dependent of the minimum distance that is seen by the robot according to its laser range measurements. So there are several issues with this modeling. First, that is there a reality gap between what the robot sees in the simulation and what the robot actually sees in the real world. So we have to tackle the reality gap problem here, and actually depth images coming from the depth sensor inside Pepper are often really corrupted, even in indoor environments, and there are many noise, mixed and lost pixels, and as it is hard to actually recover that information, we opted to actually corrupt ideal images coming from the gazebo simulator to make them more similar to the actual images that the Pepper robot sees in the real world. So what we did was to actually model some kind of heuristic noise according to the location where the lost pixels are often present in real depth maps coming from the Pepper depth sensor. So what we did was cutting edge detection using both simulated RGB and depth cameras coming from gazebo to create a mask of noise. And then we just apply this mask of noise on the simulated depth image to make it similar to the real depth image, and then just used in-painting and resizing, so both simulated and the real depth image actually have a actually are more similar in order to bridge the reality gap. As for the observability, laser measurements from the Pepper's robot laser in its base, they're really sparse. So we wanted to virtually augment the resolution of that sensor. And what we did to tackle that issue was to go through a naive approach, but just integrating laser range measurements as a point cloud through time, and filter non-coherent points, so the policy will be able to actually react to dynamic obstacles, even though it will be trained using static obstacles. And we actually limit the integration of such representation to only 6.5 meters away, since otherwise odometry will constantly integrate errors in time. The problem with this is that the obtained local map, if we can call the representation as a local map, it's a size variant in time, and we can't actually feed such representation to a neural network directly. So what we did here was to fuse all this information from the steady space that the robot was actually seeing, was using a multimodal neural network architecture, and we took a module coming from PointNet for processing the local map. So we have an encoder for the image, a PointNet module for the local map, and a simple encoder also for the retroalimentation for the odometry, for the velocities which are estimated using odometry. And we train the system using deep deterministic policy gradients, so their representation here in the slide are actually corresponds to two independent neural networks that actually share the same architecture, but are trained simultaneously. So what we do with the pointed module is to actually process every 2D point in the local map separately with the same fully connected layer, and we stack all the features resulting of this processing to then use a max pool, and that way we can have always a fixed dimensional representation, and we can then feed the concatenated features into an STM to actually be able to integrate information through time to estimate the actual state of the robot with several observations. The experiments we conducted were first to validate the approach of using a local map, and also to validate the whole system with his multimodal characteristics. So we conducted 3 experiments. First, we trained in a simple environment which only consisted in people because we only gave the robot 2D perception that experiment, and we compared how it will perform using laser integration against just using normalized or raw laser measurements. And we also conducted experiments using complex environment where there are tables, because tables, the collision geometry of tables is not, of that specific tables is not possible to estimate their geometry, their collision geometry by only relying on 2D perception. So we actually need the depth camera. The results we got are in there. We used as a metric for performance the average return over episodes, which is just like the sum of instantaneous rewards, and the average speed, as that was the main objective of the design of the reward function we wanted to make. And we got good results. It is clear that using the local map we proposed clearly helps the robot, the policy, and the simulations to get a good reward. And well, the results here are taken from 10 independent trials. So there are 10 independent neural networks that were trained, and we are showing the average reward, where performance is measured every fixed number of time steps without using any exploration strategy. So we have a little demo here. So here is a real-world validation of our system. We have a paper. You can see the local map and the processed depth images that the robot sees in an environment which is clearly different from the simple simulation environment that the policy was trained on. And surprisingly, the performance of the robot was quite good, even though, as you can see, the environment has as many objects that were not present during training. I'm going to skip a little bit since because of time we have. We can see here another experiment. I'm going to skip a little bit. So, for instance, here we can see that multimodality actually works, because that thing there, that yellow thing in the floor, it's not. It can be seen by the depth image. However, the information provided by the laser and the local map actually helps the robot to avoid it, and it effectively plans a trajectory through collision-free paths, traversable paths, autonomously. I don't know how to do it again, so I'm just going to continue. Discussion is, well, laser integration is actually not perfect, obviously, because we're only relying on odometry. But certainly we can use some proper point cloud registration to get a better local map. We actually plan on extending this system to navigation, visual navigation, but we certainly will rely on a proper localization system, as using odometry by itself wouldn't be a good choice. And as for onboard implementation, the neural networks we have there, we only need the actor network for the inference time, and by itself it only weighs 25 megabytes. It's a really, really tiny network, but gets the job done. So it's certainly possible to actually implement this on board, and as the actions are taken every 400 milliseconds, it is possible also to have this up and running in Pepper as an additional security system. And the conclusion of the works, well, the main contributions we did in this year paper are, well, a successful approach trying collision avoidance for the Pepper robot using a multimodal deep reinforcement learning. We propose a novel way to use non-fixed dimensional and ordered sets of points for RL applications, and we propose also a simple yet effective preprocessing stage to bridge the reality gap between simulated and real depth images. Well, future work, I already said this a little bit, but we also plan to extend the local map to 3D local map, as the PointNet module we use naturally extends to 3D points as well. Well, thank you very much.
Thank you very much, Francisco.